Hello everyone. In this video, we are going to talk about the direct methods of solving for a set of linear equations. So if you have a set of equations like ax equal b, where a is the coefficient matrix with known values and b is the right-hand side vector with known values, and the goal is to find x, then there are two categories of solutions. The first category is called direct methods. The second category are called iterative methods. In this video, we are going to focus on the direct methods, and in the next video, we are going to focus on the iterative methods. And here we assume that the set of equations is a square. So the number of unknowns in X is the same as the number of equations that are in the rows of AX equal B. So we are looking at the set of equations that is a square, not over, not under constraint. And we assume that this matrix, coefficient matrix, has a non-zero determinant. So determinant of A is not equal to 0. Therefore, there is a unique solution, and the goal is to find that unique solution. So how do we find it? And before I do that, you might say, why would you need a numerical method for finding the solution? Don't you have analytical solutions like the Cramer method, right? You know, in the Cramer method, so basically for each component in the X, right? So if AX equals B, then for each component in the X, you are going to basically do a determinant of a matrix which is A, except the ith column of that is replaced by B and divided by determinant of A, correct? So if you call this AI, where, as I said, AI means the ith column in A is replaced by vector B, right? So that's the Cramer method. And you can do that, right? And that gives you the exact analytical solution for each and every one of the i's. Why don't you use that? The problem is this is really good and works perfectly when the number of unknowns and the number of equations is small. You can easily calculate a 3x3, 4x4 determinant, and it's not really hard. But if you have 2,000 equations and 2,000 unknowns, which happens a lot in engineering, let's say, for instance, a finite element analysis problem or anything like that, that is not easy to calculate the 2,000 by 2,000 determinants, okay? This is going to take a lot of time. So size and complexity is one of the main motivations to use some numerical methods for solution rather than calculating these big determinants. And as I said, in lots of problems in finite element analysis, computational fluid dynamics, CFD, structural, and so on, you're going to get a lot of equations and unknowns. And the other one is computational efficiency. As I said, some of these numerical methods that we're going to learn, they solve these big equations a lot faster because they are designed to use the sparsity of the data, symmetry of the data, and so on. And sparsity means, for instance, in your coefficient matrix, you have a lot of zeros, which again happens a lot in finite element analysis. So they are designed to take advantage of that, some of them, and they can solve it a lot faster. So what are these two categories? As I said, direct methods, which we're going to focus in this video, they get the exact solution on only a few finite number of steps. So they don't need a loop that keeps going. In a few steps, typically, they give you the answer. And the main methods are Gaussian elimination, Gauss-Jordan elimination, LU decomposition, and Choleski decomposition. Okay, so these are the things that we're going to look in this video. And then in the next video, we are going to look at iterative methods that they need a loop to go and finally converge to the solution. And they are really good when the number of equations and unknowns is very large. Then in the next video, we're going to look at Jacobi, Gauss, Seidel, then SOR, and conjugate gradient. So let's today focus on these four direct methods, which takes only a few steps. Gaussian elimination. What is this? So here you have a set of equations. Let's say, for instance, this guy here, 3 equations and 3 unknowns. And the way you solve it is you form basically the augmented matrix, which is A and B. So you put A and B in one matrix. In this case, it's going to be a 3x4. And then you turn the A portion of it into basically what we call an upper triangular form. Okay? So you try to convert these three elements into 0. If that's the case, then this new number, whatever it is, times that variable, which is z, is going to be this new number. So your last equation will only be one equation and one unknown. So you directly solve z from that, then plug it back in the second equation, which has z and y, and solve for y. And then once you have y and z, you go to the first equation, which also has x, and solve for x. And that is what we call back substitution. Okay, so in this case, how do I do that? Well, let's take a look. So this is done by row operations, by elementary row operations and pivoting. So in this case, what I need to eliminate is these two numbers. First, I want to turn them into 0. So for that, I divide this number by the diagonal 1, 1 element. So I divide A31 by A11, and this ratio is -1. Okay, then I multiply row 1 by a -1. I multiply all of it by a -1 and subtract it from the third row, or in this case, I can simply just add them together. So if I add row 1 and row 3 together and place it back at row 3, what would you get? Well, in this case, you get the 2 plus -2, you get the 0, then you get the 1 plus 1 is a 2, -1 plus 2 is a 1, and then for the last one also you have to add 8 and -3, which is a 5. So right now you see two of them are turned into 0. The last thing you need to do is to take care of this one. And for that, you use the diagonal above it, which is 2, 2. So you divide 2 by 0.5, and the ratio is 4. So this time you need to multiply row 2 by a 4 and subtract it from row 3, okay? So what you need to do here is basically for row number 3, you need to subtract it from 4 times row number 2. So row 1 is gonna stay whatever it was. Row 2 also gonna stay whatever it was. Row 3, 4 times row 2 is subtracted from that. So here you get the 0, here you get the 0, here you get a -1, and here you're gonna get a 1, correct? And so this is it. This is your last set of equation. Now, if you look at it, this last row will tell you that -1 times z equals 1. There we go. So z is -1. Okay, so z is -1 here. Seems like I made a typo. So z is -1, not +1. Z is -1. Now you go back to the second row. Second row says half y plus half z equals 1. And z is already -1. So from here, you can see that y should be 3. Correct? Because that's 1.5. This is -0.5. You get +1. And then you go to the first row, and the first row says that 2x plus y minus z equals 8. Now that you have x, y, and z, you plug it up here, and you can solve for x, and x is going to be 2. And there we go. So this is called back substitution. So you convert your coefficient part of the augmented matrix into upper triangular, and then you use back substitution. That is what we call Gauss elimination. And in MATLAB, this is done by the backslash operator. So if I show you in MATLAB, here I have a system of equations with 2,000 equations and 2,000 unknowns, and A and B are coming from random numbers. In MATLAB, the solution is coming from A/B. That is called optimized Gaussian elimination, and it's optimized so it does it as fast as possible. And here you see I get the solution and I put a tick and talk to see the runtime, and you see the runtime for 2000 equations and 2000 unknowns was only about 244 milliseconds. Okay, about a quarter of a second, which is really fast. Okay, so this command is doing a great job. Now you might say, can I use the inverse matrix? Yes, of course. I mean, you can always say that x equals a inverse times b, but the problem lies is this inverse. Here your matrix is 2000 by 2000, and finding the inverse of that is going to take a lot of time. But if you say x equals a backslash b, this is solving it with Gaussian elimination, which is a lot faster than a inverse b. And if you want, I can put another a inverse b here for you, right? And I can show you that if I do it with a inverse b, right, it is not going to be as fast. Let me just add it for the sake of, so analytical solution with inverse. So here I do another one, and this time I say this is inverse of a times b, and I call it x of inv, and then I call this t0, and then show here t0, and then say using the inverse of coefficient matrix. Okay, so if I just run this portion for you, let me just run this portion because I don't want to run the whole thing again. So here we go, run it with that, and you see in this case it's a little bit more. It's about like 305 or 306 milliseconds, but the more we basically the bigger the set of equations is. So if I, instead of 2000, I make it 20,000, you see the difference between the inverse and this Gaussian elimination starts to grow. Still 2000 is not super bad, and the numbers are not super large, so still the difference is not big, although you still can see Gaussian elimination does a better job, but over bigger sizes, you definitely are going to see the difference here. Okay, so one thing I need to emphasize here is pivoting. So you know that when I do this row operation, I always divide the number that is off diagonal by the diagonal, find the ratio, and multiply that ratio by one row, add it to the other row. The problem happens is when this diagonal number is 0, then you cannot divide the off diagonal by 0. You get an infinite ratio. So what would you do in that case? You do what we call a pivoting. So what does pivoting mean? So let me show you in this case, for instance. So if in this original set of equation, this term was not there. So the first equation was y minus z equals 8. Then what you will see happening to your A matrix is this guy is going to be 0. Now, if I want to get rid of this -3 and -2 and turn them to 0, I cannot divide them by that 0 on the top, okay? So you might say, what would you do in that case? The solution is, well, of course, I'm going to swap rows before I find those ratios and I do row elimination. So how do I do it? Well, simply I can go ahead and swap, for instance, row 2 with row 3. So I just swap these two rows. Then my matrix is going to be like 3, -1, 2, -11. And then 0, 1, -1, 8, and then -2, 1, 2, -3. Okay, in that case, this one is already 0, so this is good to go. All I need is to multiply row 1 by like 2/3 and add it to row 3. So it is going to be row 3 plus 2/3 of row 1. then this guy is also going to go to 0. So a simple swapping of rows will bring that 0 diagonal to below diagonal, and that will take care of the problem. Now you might say, do you do this pivoting only when the diagonal is 0? No, sometimes the diagonal is a small number. It's not necessarily 0. You still might need to do that in order to improve the accuracy of your solution and provide stability. Like where? Like let's say this is your equation and this is your A matrix this time. So if I want to get rid of this 1 and make it 0, what should I do? I should divide this 1 by this 1 over 10,000. So basically, I should multiply row number 1 by 10,000, and with the negative, add it to row number 2. Now here, because I'm multiplying my numbers by this big ratio, there is a chance of losing my numerical accuracies because of the round-off errors, and the solution is not going to be as accurate. Another way you can look at it is if you watch my videos under the same playlist, Engineering Mathematics, there is this number called the condition number. Okay, and this condition number will tell you whether, if you provide any perturbations to your right-hand side, whether the solutions of U or to the numbers in the A matrix, whether the solution you will get will change dramatically or just change a little bit. So if this condition number is, which comes from the determinant of the A matrix and the determinant of its inverse, this number is around 1, your system is well conditioned. If it's way bigger than 1, your system is ill conditioned. Okay, so this condition number can also tell you that, but again, you can see that if I have a system like this, it's way better to swap row 1 and row 2 and bring this big number 1 here, okay, to get my job done. So that was Gaussian elimination and how to do it in MATLAB. Now, what about Gauss-Jordan elimination? So Gauss-Jordan elimination, the first part of it is just like the Gaussian elimination, but instead of converting A into an upper triangular matrix like U, you convert this A further to an identity matrix. So in original system, which is A and B, you converted into I and some new B prime. And in this case, since identity matrix times any unknown vector x is equal to x, then your solution x is directly equal to the right-hand side B prime. So you don't even need to do back substitution anymore because the right-hand side are exactly your unknowns. But that needs an extra operation to go from an upper triangular matrix A into what? Into an identity matrix A. So it needs a lot more operations, and typically that is very slow. Okay, so if I want to show you an example with numerical numbers, let's take a look at here. So this is that same system that we had, and first we converted it into the upper triangular. If you remember, we started with this, we turned this -3 and -2 into 0, and then we basically multiplied this row number 2 by a 4, subtracted from row 3. If we did that, this guy became a 0, and this one was in like a -1. But before we do that, before we eliminate these 2, since this A portion of it should be an identity matrix, first we have to take care of this -1/2 or +1/2. Because if it's identity, this guy here should be 1, it should not be 0.5. So before I do anything, first I multiply row 2 by a 2. So row 2 becomes 0, 1, 1, 2. So now my matrix is going to be like 1.5, -0.54, then 0, 1, 1, 2, and then 0, 2, 1, 5. So I turn it into this. Now I, as I said, multiply my row number 2 by a negative 2 and add it to row 3. So it's going to be row 3 minus 2 times row 2. If I do that, this guy goes to 0, this guy goes to negative 1, and this guy is going to positive 1 here, correct? So when that's the case, now if you look at the A portion, which is this part here, you see that now you have this upper triangular part, and this one is 1, this one is 1, this guy is negative 1. So before you do anything, you have to turn this negative 1 into a positive 1. So you multiply row 3 by a negative 1. That way, these two still stay at 0. This one becomes a positive 1. This guy becomes a negative 1. And now your 3 diagonals are all 1. So you are getting closer to an identity matrix. So let me rewrite it with those new numbers for you. There we go. So now you have this after several steps. Upper triangular, all diagonals are 1. Now it is time to get rid of these 3. So for that to happen, this time we go backwards up. So I divide these two numbers now by this 1. So the ratios are 1 and like negative 2.5. So here I subtract row 2 from row 3, right? So let me write it for you. So row 2 minus row 3. And then row 1 plus 0.4 times row 3. If I do that, this guy goes to 0, this guy goes to 0. And then these two will not change, okay? And this one, since you're just subtracting it, this one is going to go to a 3. And then when you multiply by 0.4, that one goes to 0. And this one, when you multiply it by 0.4 and adding it to that, that is going to be 3.6. Okay? So now your matrix, if I replace the numbers again, now it is going to be like this. And the last step that you need to take is to get rid of the 0.5 elements, the element 1 and 2. So you just need to get rid of this. Okay, and for that, as you can see, you divide that by this 1 and subtract. So it's going to be row 1 minus 0.5 times row 2. And if you do that, this guy is going to go to 0, and this guy is going to be like 2.1. And that's it. So now look at your A portion of the matrix. It becomes an identity matrix. So this right-hand side, which is 2.1, 3, and negative 1, these are your solutions for X. Okay, but clearly this going from the upper triangular to this identity matrix took a few more steps, and when the matrix size is big, that means a lot more computation. So here in MATLAB, if I want to do the Gauss-Jordan elimination, the MATLAB, there is no built-in MATLAB function. So for that, I need to use for loops, as you can see, nested for loops with ifs. And if you see, when I did that for this 2000 by 2000 equations, it took the huge amount of time, 128 seconds. So typically, the moral conclusion is the Gauss-Jordan elimination is typically not really something that you want to use in normal condition. It takes a lot of time, and there is no MATLAB command for it. There is no optimize command, and we barely use this in reality. We typically only use Gauss elimination. Okay. The next method is LU factorization, which I have a separate video on that, right? You probably have seen that video, LU decomposition or LU factorization. Here, you decompose your A matrix into the product of a lower triangular matrix and an upper triangular matrix. And for the lower one, you typically do it in a way that the diagonal elements of that are 1. Okay, so for instance, if this is your original A matrix that you started with, you break it down into the product of these two matrices. So it's going to be L times U, where L is this lower triangular matrix with all ones on the diagonal, and U is this upper triangular matrix. Okay? So you can write that L as the product of this L and U. And if you watch that video that I have on LU factorization, the method is basically, again, Gaussian elimination. So you start with row operations and turn this A prime into an upper triangular matrix U with the same way that I told you. Now, how would you find the L matrix for that? L, as I said, the diagonals of that are 1. Above diagonals are all 0. Now, below diagonals, these numbers here, they are coming from the ratios that you used to multiply each row by those ratios, add it to the other row, and get all those zeros. For instance, this element 2, 1, this 1 here, right? This guy here. Where does that come from? It comes from the ratio of this 1 over this one when you want to add a multiple of row 1 to row 2 to convert that 1 into a 0. That ratio is 1. So that 1 is going to go and sit right here. Yes? And then if you look for the other one, for instance, M31, which is this guy here, right? That comes from the ratio of this 2 over 1. And that ratio you multiplied by row 2 subtracted from row 3. So that 2 is going to go sit right there. And finally, when you get rid of these 2, 1 and 2, make them into 0, right? Remember, so you get 1, 2, 1, and then 0, and then negative 1, and we just do it. So negative 1, and then 0, then negative 3, and negative 1, correct? So now the next number you want is this one to go to 0. So the ratio is going to be this negative 3 divided by negative 1. And that is called M32, okay? And that ratio, which is 3 in this case, that is going to go and sit right here. So you see, these lower diagonal numbers are coming from these ratios. And that is how you form the L matrix. The resulting U, the resulting upper diagonal after the elimination, is going to be your U matrix, okay? So that is how you get L and U manually. But in MATLAB, if you want to do it, the command is called LU. So you just pass LU, the matrix A to LU, and it gives you L and U, as simple as that. Okay? Yes? So it works just perfectly fine. And one other thing that I need to talk about it before I say how to use it now to solve this set of equations is sometimes, as I said, because of those zeros on the diagonals, you need to do a permutation. You need to swap some rows. As I said, you need to do the pivoting. For that case, instead of A being equals to L times U, a permuted version of A is going to be equals to L times U. And this P, or permutation matrix, is the matrix that you use to swap some rows. For instance, as I said, if A is like this, you cannot divide this 1 and 2 by 0. In that case, you need to swap some rows. So let's say you want to swap row, in this case, row 1 and 2 together, right? So you want to swap these two rows. How would you do it? You pre-multiply A by this P matrix. And that is going to do the job. How? If you look here, if it was an identity matrix, so this one was 0, this one was 1, this one was 0, this one was 1, if you pre-multiply P by A, it's not going to do anything. But here, look at the way that the zeros and ones are exchanged. Look. So compared to an identity matrix, you see the zeros and ones in the first and the second row and column are exchanged. That is swapping row 1 with row 2. Now here I call it row 1 and 0, but this means row 1 and row 2, go ahead and swap them together. And it does that, so now your A matrix This row goes to the top, this row goes to the bottom, and this is your PA. Now that it is good, you can apply LU factorization on that. So PA is going to be L times U, or another way to write it is to write A as P transpose times L times U, okay? Because if P times A equals L times U, you can multiply both sides by P transpose. And it's not very hard to see that P transpose, if it's multiplied by P, the result of this is an identity matrix. So A can also be written as P transpose times L times U. Because P swaps row 1 and 2, P transpose swaps row 2 and 1. So when they multiply together, they kind of cancel each other and there will be no effect. So the effect is identity. Okay? So the way that you get LU and the required permutation in MATLAB, again, is the LU command, but this time you get 3 outputs out of it, LU and P. Good? So now that you have this, how would you use it to solve your linear equation? So you broke down your A matrix into a product of L times U. Okay, fine. How would you solve the equation? So your equation was A times X equals B. So now I replace A for L times U. So it's going to be LUX equals B. Now I call this U times X and U vector Y. So look, it's going to be LY equal B. And since L is a lower triangular matrix with a bunch of ones on the diagonal, solution of that is simply forward substitution. So I start solving from the top element in Y, and then because it has one equation, one unknown, then I go to second row, then I go to third row, and I solve elements of Y from the top to the bottom. So that is what we call forward substitution. So I got the Y. Fine. Now that Y is found, U times X equals Y. And Y is known and U is known. Now U is an upper triangular matrix. So that means the first row has a bunch of more equations and unknowns. The second row has one less. The third row has one less, and so on and so forth. So this time you can start at the bottom equation and find the last element in X, and then go upward. So that is what we call the backward substitution, right? So first you solve for Y from this equation, and then you plug that Y into the bottom one, and then you solve for what? For the X. Done. So if you can break down A into L times U, you can solve for X in a forward followed by a backward substitution. And in MATLAB, if you want to do it, you can just do 2 backslash operations, right? Because backslash is doing either forward or backward. Yes? So the first operation for you is Y equals L backslash B, and the second one is X equals U backslash Y. Good, and that gives you the solution. Now, if there is the extra P, if there is a permutation P, then what you would do is, because this time you have P transpose times L times UX equals B, you have this, right? Still, you call this U times X equal Y. So now your first equation is P transpose L, the whole thing, times Y equals B. So if you want Y, you have to basically use P transpose L and B, and that is your first operation. It's going to be L backslash PB, okay? And you might say, is this the same as that? Yes, because from here, you can multiply both sides by a P. Remember, PP transpose is identity matrix, so you would get LY equals PB. So if you do L backslash PB, that is your Y, and then U backslash Y is what? X. So if you need a permutation matrix, use these 2 lines as opposed to these 2 lines. And that's it. Okay, and here I have used that LU decomposition, assuming that there is a need for P, and I found the solution, and look at how fast the solution took. Only 113 milliseconds, which is even faster than Gaussian elimination. Okay, so you see LU decomposition can do a relatively good job, okay? Yes, it's a good general solver, but Gauss-Jordan was extremely slow. And finally, the last thing we want to look at is called the Cholesky decomposition. Okay, and this one is for a specific scenario where your coefficient matrix A is positive semi-definite. So A cannot be any special, any matrix. It should be a special matrix that is positive semi-definite. If it is, then A, instead of writing A as L times U, A can be written as L times L transpose. What's good about it, the good thing is you don't need to find two matrices, you just need to find one matrix and the transpose of that. Or A can be written as an upper triangular transpose times upper. Here I used R, but you can use U. So either of this is valid as long as your matrix is what? Basically symmetric positive definite. Symmetric positive definite. And in many cases in engineering, like finite element and so on, many times this A is a symmetric positive definite matrix. Okay, for instance, you know, the mass matrix or the stiffness matrix in many finite element problems, these are symmetric matrices, and these are basically positive definite matrices. So if I need to work with this kind of matrices, and I have a system of equations like, for instance, K times displacement equals force, then my coefficient matrix is positive, symmetric positive definite. So if I want my displacements of the node, guess what? I can use Cholesky decomposition. Now, how would you find the L matrix or the U matrix for this scenario? Well, this is the way to do it. So if you want the L, let's go with this format. Each diagonal element of L is the square root of the diagonal element in A minus summation K goes from 1 to I minus 1 of the element in that specific row, all squared, added together. So this first gives you the diagonals in the L, and then you can find the off diagonals in the L based on this formula. So once you have the diagonals and off diagonals in the L matrix, that's all you need to do. And now if you find them, the question is, how would you solve? Well, the answer is this. So L transpose times X equals B. So here you go ahead and call this guy a Y. So your first equation is Ly equals B. And of course, you can solve that with forward substitution. Then L transpose X equals Y. And this one will be a back substitution because L transpose is really an upper triangular matrix. And again, a forward and backward will do the job. Why this is good? Because you only calculate one of them one time, so it should be faster than the LU factorization. And if you see in MATLAB, basically the runtime for this specific A matrix that I created, positive definite symmetric, the time was only 55 milliseconds, about half of the other one, half of the LU. Now, two things. One, how did I get my matrix? L, or R in this case, it comes from the built-in function CHOL. So you just pass the coefficient matrix to it, and it gives you L or R that you want. And here you can do forward and backward substitution and get your answer. Now, how did I make sure that the coefficient matrix is symmetric positive definite? Because here my matrix to start with was a random matrix. It's not necessarily symmetric or positive definite. The way I forced it to be positive definite and symmetric is I form a new matrix, which was a transpose times A. You know, for any matrix A, if you calculate a transpose times A, this is a quadratic form. It's always positive definite. and it's always symmetric, because if you take transpose of that, the transpose of it is going to be the same thing itself. Okay, so it's symmetric and definitely positive definite, and that's exactly what I did over here in the code. And you can see that this method is really the fastest as long as your matrix is SPD. Good. So this is regarding MATLAB and how this chol command is working. Okay. Yes. So before I finish this video, I want to show you how to use that chol command in MATLAB. And then for a specific example, which is this A matrix, I'm going to show you how to get the lower or the upper triangular version of it. Okay. So if I want to write it as like this or like that, how do I find L or U? So here I type that matrix in MATLAB. Okay. And if I just give it to the command chol, the default is the upper triangular matrix. So it gives me U, right? If I want the lower, then I have to give it the option lower. So look here, I have to say this. I have to say, hey, give me the lower version and let me call it L instead of U. There we go. And this is the lower version of it. Okay, so by giving it an option, you can determine whether you want the lower or the upper triangular. Now, if you want to know, for instance, so here, look at the numbers are 2.5 and 0.5 and so on, which is basically this. If you're wondering how this A was written as L transpose, where L is this matrix, could you show me how to use these formulas? Yes. So let's just look at one of them, for instance. So let's say this one here. How did I calculate that? So here we go and say L11. So plug in I of 1 here. Right? L11 is square root of what? A11. And then minus summation from K of 1 to I minus 1, which is 0. And summation cannot go from 1 to 0. So this whole summation is going to be 0. So it's just simply square root of that. And of course, the square root of 4 is 2. So you might say, how would you find the rest of it? So I need to find these other elements. And in this case, if I look at the formula, you can see that here it says J goes from I plus 1 to N. So if I is 1, J is going to be 2 and 3 in this case. So this is going to give me L21 and L31. So L21 and L31 for I of 1 can be found from this formula. And if I do that, clearly, you see that, for instance, it said that, let's say 2,1, this is going to be A21. And then this summation goes from K of 1 to I minus 1, which is 0. So that summation does not exist in this case. So this is going to be divided by L11. And then the next one is going to be A31 divided by L11. So what I need to calculate for them is A21, which is this, divided by L11. So you are going to get a 1/2 for this, or 0.5. And the other number is also 1 divided by 2, right? This number, and that is also going to be 0.5. And that is exactly these two numbers that you can see. Okay, and then you can go to the next row, and for I of 2, this time you first calculate this, then you calculate this one, and finally for I of 3 you calculate this one, and you're good to go. Okay, so you see this is the formula that you have. For the 3 by 3, L1 is the square root A11, and then L21 and L31 are these two formulas, and if you want I can write the rest of them for you. So L22 is going to be square root of A22 minus L21 squared. Then L23 is going to be A23 minus L31 times L21 divided by L22, and finally L33 is going to be square root of A33 minus L31 squared and then minus L32 squared. Okay, and then you can find all of the L components as I said here. And as I showed you in MATLAB, this is extremely fast for when the matrix is positive, definite, and symmetric PSD. And this is the code for it. So hopefully the video was useful to you, and I'm gonna share also this code with you on the video description, and I'll see you in the next video. Thank you.